Tutoring SAT video, and today we are going to cover one of the most feared concepts in all of the SAT. Hello everyone, and welcome back to another framework tutoring video. Today we're going to go over one of the most feared concepts on the entire SAT. By the screen, you can already probably tell that it's geometry. So I decided to start off this lesson with this formula sheet. This formula sheet will be provided to you for the no calculator and the calculator section. It's in the front. And these just give you some basic formulas that are often used in the SAT. So circumference of circles, areas of triangles, angles, cylinders, cones. Now a lot of questions that I get asked is about whether you should memorize these formulas. And I think that there's kind of a really nice fine line in between that you need to fill. Now, I don't think it's like super important to know some more obscure things on here, like the special right triangles. Like it's obviously really great if you do, and you should still have a basic idea of how they work when you go into the SAT. But for me personally, I didn't know all of these I knew most of the formulas on here. You should be able to know most of the formulas on here, but I didn't know the formula for the special right triangles, or I didn't know this formula for a pyramid or a cone, so I just had to look back really quick and solve the problem using the formulas that they give you. So what I think is that some of the more obscure things on here, like volumes of a cone or a pyramid or special right triangles, it's not like super mandatory that you know, but it is mandatory that you A, know how to use them, and B, all the other ones on this formula list you should be very comfortable with. Area, volume of a square, a rectangle, a circle, a triangle. These are things that you should do so often that you should already know them even without looking at the formula sheet. All right, so before we actually get into these problems, we are going to get started by Alright, so before we go into problems, like always, we're just going to do a quick mini lesson on everything that is covered by geometry in the SAT. There's a little bit to cover today, but as always, if you have any questions, feel free to contact me anytime, and also make sure to practice on the SAT, because no matter how much concepts we go over, there's going to be some things that you just can't know or can't tell unless you actually do the work. Okay, so the first thing is going to be the midpoint formula and the distance formula. The midpoint formula and distance formula are two very important concepts on the SAT. So let's assume that you have a line. Let's assume that you have a line that's like this. Oh, actually, I did not mean to do that, but that achieved what I wanted to, so I guess that works. So let's assume you have a line. This is the x-axis, this is the y-axis, and let's say this is 0 and this is 12. Now, what if you wanted to find the point on this graph that's the middle of this point? So everything on each side is the same. Now, for a problem like this, it's honestly pretty easy, and you could do it like by probably just looking at it. Sneak peek, the answer is 6. But in a lot of cases, finding the midpoint can be a little bit more difficult because it's either going to give you a really large value, and also sometimes the point's not just going to have an x value, it's also going to have a y value. So you're not just going to have to know what the middle is for the side, like this, but you're also going to have to know what the middle is for the top. So there is a formula for this, and it's a pretty easy formula to memorize, and you should definitely have it memorized. And no surprise, it's called the midpoint formula. And the midpoint formula is x1 plus x2. Divided by 2. And then for the x values, and then for the y values, it's y1 plus y2 divided by 2. The most important thing to remember is that these formulas and these x points are just the 2 points that you're trying to find the distance on. And if you really think about it, these formulas do make sense. If you divide this up into 2, and these are equal, then the point that's left just has to be the one where it's a midpoint. And the same with the y. So just keep in mind this midpoint formula, because a lot of questions will ask you to find the middle of a shape, or even in a graph, it might ask you to find the middle of a graph. This is the formula to use. The next thing we're going to look at is also a very important formula that is not just important in geometry, but could also be used in some other real application SAT questions. And that is the distance formula. Now, you guys have probably already heard of the distance formula and also probably already of the midpoint formula, but please, please, please know these formulas by heart for the SAT. The distance formula, like its name suggests, just calculates what the distance of this is. And the formula is x2 minus x1 squared. Let me write that again so it's a little clearer. Sorry about that. x2 minus x1 squared plus y2 minus y1 squared. And all of that is under a square root. Once again, same as the midpoint formula. This would be x1, this would be x2. Doesn't really matter what order you do it in, as long as you keep it consistent and you do the y1 and the y2 with it. They're just the 2 points that you're trying to find the distance between. So yeah, that's just the basic distance formula. The next thing that we're going to go over is angles. Angles are very important in the SAT. You guys already probably know what an angle is. They're shaped like this. It's just like this area between two lines and the, I guess, configuration that it holds. So this could be an angle, or this could be an angle. And yeah, so the SAT covers a little bit on angles, so we're going to go over everything that you need to know. The first thing is the types of angles, and hopefully you already know this, but there's 3 main types of angles. You have acute angles, obtuse angles, and right angles. An acute angle is any angle where the degree is less than 90 degrees. So what I mean is something like this would be an acute angle because 90 degrees is right down the middle here, like this. Since it's smaller, this is definitely an acute angle. As you've probably guessed by now, an obtuse angle is just any angle that is larger than 90 degrees. So if the 90 degree line goes down here, sorry about that. If the 90 degree line goes down here, since this is larger, this obviously has to be an obtuse angle. So it'd be a degree that's greater than 90 degrees. The final thing is right angles. Right angles are angles where the degree is equal to 90. So when it's exactly 90 degrees, it is a right angle. You will also know it's if a geometry problem gives you a right angle because there will be a square in between here. If there's a square in between this point, then you automatically know that it's a right angle. All right. I also just think one important thing to note that you will probably need to know is, let's just assume you have a straight line. That's not completely straight, but let's just assume it's a straight line. This entire thing is 180 degrees. If you divide it up into half, let's say these are right angles, 90 degrees. As you can see, kind of makes sense. Just something to note. 180 degrees is a very important degree value that you'll use a lot on the SAT. But it's not just important sometimes to know the types of angles. It's also about how they're made using different lines. And the SAT will like to teach you on relationships between different angles. What I mean by that is, let's assume these 2 lines are parallel. That means that they're completely straight, they have the same configuration, they'll never ever touch if they stretch on to infinity. And let's assume that you have a slanted line going through these parallel lines. Now, just putting this one line through these 2 parallel lines creates a bunch of new angles, right? You have 1, I'm just gonna mark these, and then 5, 6, 7, 8. You already have 8 angles just by adding this line through. And what's important to note is that a lot of these angles have very, very interesting and similar relationships. The first thing are vertical angles. Vertical angles are angles that stare directly at each other. What that means is something like this and this. So 1 and 4, 3 and 2, 5 and 8. Oh, did not mean to do that. 5 and 8, and then 7 and 6. Vertical angles are equal to each other. That means that here, angle 1 is equal to angle 4, angle 3 is equal to angle 2, and etc. The next type of angle we need to know are corresponding angles. Corresponding angles are angles that are, when it's through a parallel line, that represent the same angle position, just in a different location. That might have sounded a little bit confusing, so I'm just going to go through and explain that to you. So let's assume we have this original configuration that we made before, right? Corresponding angles, in this case, would be 1 and 5, because they are in kind of like the top left corner. They represent the same angle through this line. It's important to note that these concepts and properties only apply if these two lines are parallel. If these two other lines are perpendicular, then, or like they'll eventually cross with each other, then we cannot make these conclusions. So remember, this only applies if the two lines are parallel. But if they are parallel, corresponding angles are also equal. So angle 1 is equal to angle 5, angle 2 is equal to angle 6, angle 7 is equal to angle 3. And also just this sign, sometimes used on the SAT, that just means angles. And yeah, so that's just the basic idea behind, oh, sorry, did not mean to do that. That's just the basic idea behind corresponding angles. But obviously, there's more that we need to cover. The third type we're going to look at is alternate interior angles. Alternate interior angles, as their name suggests, are angles that are inside the two parallel lines and the line that goes through, and they're ones that alternate with each other. So they're on the opposite sides. So, for example, 5 and 4 are alternate angles, while 3 and 6 are also alternate angles. Alternate interior angles are always equal as well. So 3 is equal to 6, 5 is equal to 4. Just a quick review, all three that we've gone over so far, the types of angles, are all the same to each other. So it could be important or maybe even helpful to remember both of them in groups. If it's a vertical angle, if it's a corresponding angle, or if it's an alternate interior angle, then it's all the same. And we also have one more type that is the exact same, and that is alternate exterior angles. Can you guess what that is? You probably can. They're angles outside that alternate. 1 and 8 are equal, and 2 and 7 are equal. So these are all the 4 types of relationships that you'll be tested on that say that angles are equal. But sometimes there's also relationships that don't necessarily just deal with them being equal. These cases are known as first same side interior angles. We already know what interior angles mean. It means they're inside here. But if it's a same side, then it means it's literally on the same side. Same side interior angles add up to 180. That means angle 5 plus angle 6 will equal 180. And angle 3 plus angle 4 will also equal 180. And if you think about it, this should make sense because we already talked about how when there's a straight line, the angle degree of that straight line is going to be 180. So since those two interior angles make up a straight line, then it means that it has to be 180 degrees. Also, just another term to throw out there that can be used on the SAT, the difference between complementary and supplementary angles, these are just fancy names. A complementary angle means that it's 90 degrees. A supplementary angle means it's 180 degrees. So you could say that that same interior angles, so interior angles that are on the same side, are supplementary because they will always add up to 180. All right, the next type that we need to look at is angles that, here, let's see. The angles that are outside, so that are exterior. Exact same, these add up to 180. Basically, any two angles that add up to a straight line will always equal 180. All right, so now we've basically gone over everything you need to know about angles. The next thing we need to cover is polygons. Now, there's a lot of questions about what a polygon actually is. And basically, a polygon is just any shape that is closed off. So something like this would not be a polygon, but something like this is technically a polygon. Now, on the SAT, they are definitely not going to ask you a question about this thing, but the SAT likes to use a couple very standard polygons that you probably already know about, and those are just your classic circle, triangles, squares, and sometimes they'll spice it up with like a pentagon, and they'll also have rectangles, and they might have trapezoids, just basic stuff like that. All right, the most important thing to remember about polygons is that all polygons have their angles add up to 180 except for a circle. A circle is the exception. All of this is 360 degrees, but for polygons, when you add these up, for triangles, for squares, for pentagons, it's always going to equal 180 degrees. So an important thing to note is some angle values. There's only really two that you need to know, and then you can use those to kind of come up with other ones. In a circle, 360 degrees. In a triangle, 180 degrees. In a square, 90, 90, 90, 90. So 360 degrees. Same with the rectangles. It'll always add up to 360 degrees. And it's just something that's important to keep in mind, because in the SAT sometimes it'll give you like, we'll look at a problem like this, but it'll give you like two of the angles or one of the angles, and then there will be a variable, and you have to like use the information that you already know about this to actually solve the problem. Yeah, so we're gonna go through some of these more common polygons and see what they ask you about. Also, one last thing, trapezoid always has 360 degrees as well. All right, cool. So let's get started. The first important type of polygon we're going to look at are triangles. Your great, amazing triangle. Now, there's a bit of concepts that the SAT covers on triangles. The first we need to know is the different types of triangles that actually exist. There are three main types of triangles. There are equilateral triangles, isosceles triangles, and scalene triangles. You probably already know this, but equilateral triangles, this is a terrible equilateral triangle, by the way, but let's assume that it is. You can note an equilateral triangle if it has two dash marks on each side. That means that all three sides are equal. Now, an isosceles triangle will have two of these. These two sides are equal, so it means that two sides are equal. If it's a scalene triangle, no two or more equal sides. So each one side has a unique length. So equilateral, isosceles, and scalene. There's also another way to classify triangles, and that's by angles. Sorry, triangles, and that's by the angles, not by the side lengths. So the first type is known as an acute triangle. Now, I don't know if I have the artistic skill to draw an acute triangle, but an acute triangle just means all of these three angles that make up the triangle are less than one. Sorry, they have three angles, and each of them are less than 90 degrees. You can have a right triangle, and then one of them has 90 degrees. And then if you have an obtuse triangle, it means it has one angle that is greater than 90 degrees. So remember, acute, three that are less than 90, right, one that is 90, and obtuse, one that is greater than 90. So those are the three main types of triangles, both by triangle side and by triangle shape. The next concept you need to know about triangles is how to calculate their area. Now, there is an equation for this. The area of a triangle, 1/2 base times height. Probably already know this. The base of the triangle is the base. Just one side that's at the bottom that you choose to use. The height of the triangle is its height, so how tall it is. So let's assume this is a right triangle. The area would be 4 times 3, which is 1/2, 12, 6. So the area of a triangle is calculated using this equation. All right. So that's basically most of everything we need to know about circles. No, sorry, not circles, triangles. I'm speaking a little bit too early. Next, we are actually going to go into circles. Now, circles are a very interesting shape. Always have 360 degrees. They have a center, and then they have the circle thing that surrounds it equal distance on each side. So there are a couple terms about circles that you need to know. If you actually, sorry, did not mean to do that. If you actually want to be confident on the SAT. The first is the center. We already looked at that. The second is the radius. The radius is the distance between the center to one side. So this is the radius. The diameter is the entire line cutting through the center of the circle. So this entire thing is diameter. As you've probably noticed, diameter is always just 2 radius because it's 1/2 plus the other half. The third thing that we need to know about is circumference. Circumference, is just the distance or the length of this entire circle. So the edges of the circle, let's imagine you have this circle and then you like flatten out the sides of the circle and make it into a line. How long would that line be? That's the circumference. And the circumference of a circle is calculated by this equation. It is C equals 2 pi r or pi d, because 2r is the same as d. If you don't know, pi is just a constant that we use for circles, and it's a very long number. But let's see how many digits I know. It's 3.14159265358979, and then you just keep going. The only digits you really need to know is just 3.14. You can make a calculation using 3.14. And yeah, basically pi will always be a constant no matter where it is used in the equation. The fourth thing that you need to know for circles is the area. And as you can imagine, area is just the same thing as always. It's just like the shaded region inside. So the area of a circle is calculated by the equation pi r squared. And r is the radius. And yeah. And these concepts will basically cover almost everything you need to know about circles. But there's one other important concept that we need to talk about, and that is angles inscribed inside of circles. So now we're combining two ideas together. So let's say you have this circle and there is an angle inside of it. This angle is inscribed in the circle because it is inside the boundaries of the circle. And let's say you have a center point, so there's a center of the circle, and there's another angle here. So there's two angles here. Sometimes the SAT will give you questions like this, and we'll go over one like this, and a lot of the times, kids just freak out, and I don't blame them, because if you look at a problem like this, like, it looks pretty difficult, because where would you even get the values of these angles, and how would you even be able to solve them? But actually, it's a lot more simple than you might imagine. There's very just simple equations that you can use to, I guess, solve these problems. Okay, the first thing we're going to look at is comparing this angle, so the inscribed angle, and the angle that the center makes. Basically, what happens is, let's say this angle is x, and this angle is y. X is always equal to 2y. Right? Very, very simple. So if the inside here, if this was 50 degrees, this would be 100 degrees. And also, that's really important to note because another concept is that if you have a center angle, then the arc that it encompasses, so the circle arc, the curve, is the exact same degree value. So since this is 100, this is also 100. So you could also view it as if you have an inscribed angle. This area is going to equal twice of the degree values here. All right, cool. So now we've basically gone over, and that is the idea of sine, cosine, oh, sorry, had the wrong thing clicked, cosine, and tangent. So if you guys are in any algebra or geometry or trigonometry especially, you guys have probably heard of these terms before. If not, you might have heard of them, and they might even seem a little scary to you, and I can't blame you, because if you've never seen any of these things before, they just look super random, and obviously they look like things that I guess you just never really see normally. So, how do you solve these problems, the sine, cosine, and tangent problems? Well, the biggest thing to remember is that sine, cosine, and tangent, all that they are is that they're a fraction. So there's going to be something on top, something on bottom. And it's a fraction based on a right triangle and a reference angle that's given, and then the lengths on each sides of the triangle. So what I mean by that is, let's look at an example. Let's say I have a right triangle. Remember, it has to be a right triangle. And let's say the lengths here are 6, 4, and 3. And let's say it gives you this angle, and it'll usually call it a variable like theta. Theta is just a variable. And it'll say, find sine of theta, or cosine of theta, and tangent of theta. This looks a little scary, but just keep in mind that all this means is to find a pattern and find a ratio. So what is that ratio? Well, the tool to remember that is something called SOHCAHTOA. If you've heard of this, you probably already have this ingrained in your mind. If you did not hear of SOHCAHTOA yet, please, please, please remember this concept. It'll be very important, not just for the SAT, but for every other math that's ahead of you. So what this stands for is sine opposite hypotenuse. What that means is that when you ask to find the sine ratio of an angle, you go to the angle, you reach to the opposite side, that's your top value, over your hypotenuse, which is the longest side on a right triangle. Oh, not 6, sorry, not 4, it's 6. That means the sine for this equation is 2 over 3. Cosine, oh, did not need to do that. What I was saying is cosine is adjacent hypotenuse. So what you do is you find the side that's nearest to the angle that is not the hypotenuse, and then you put the hypotenuse, so it's 1 over half. Tangent, you're probably already guessing, opposite, adjacent, so it's 4 over 3. And that's literally all sine, cosine, and tangent are. You'll just be asked to find these ratios and plug them into the equation. One other thing I want to keep in mind about sine, cosine, and tangent is that there are a couple properties. The first property is that if you are given a sine value and a cosine value, and let's say the sine value here is something like 36. That's the reference angle. So that's the reference angle. That's theta. This is equal to 90 minus 36. So that is 54. Cosine 54. So this is that complementary angle structure. What this represents is a representation between complementary angles. So this works only with 90-degree angles. If cosine of something then sine is always going to be equal to that 90 minus that cosine. This applies for anything. So cosine 1 is the same as sine 89. This pattern is very important for the SAT, and I believe there's a problem we're going to go over that shows this exact thing. Final thing about sine, cosine, and tangent, there's something called trigonometric identities, which are just things that are held to be true. Just remember, sine squared theta plus cosine squared theta, these are any angle values, so this can be anything inside, but they have to be the same, always equals 1. Keep this in your memory, because sometimes the SAT will show problems that are related to that, but they won't tie it in, so people get confused and sometimes panic and don't do as well as they normally would. Okay. So now that we went over, Alright, so we went over this concept of sine and cosine's degree relationship when talking about complementary angles, but it also applies for supplementary angles if it's 180 degrees. So that's the only property you're going to need for this question. This will equal this. Will equal, wait, no, not that, sorry. That, so this will equal this because these two add up to 180 degrees. So if you subtract them from each other, your answer is 0. All right, so the next problem is, sorry about that. Did not mean to do that. All right, 28. The figure represents a rectangular pool with a width of 20 meters and a length of 25 meters that's surrounded by a concrete border with a uniform width of X meters. If the combined area of the pool and the concrete border is 546 square meters, what is the value of X? All right, so what we are trying to do right now is find the X here that separates this. So as always, we are going to draw a diagram first. Please forgive my terrible drawing skills, and after you make a drawing, you write all the information that you know. So you have this pool, and you know that this distance between it is X, but you also know that the pool goes up 25 meters, goes sideways 20 meters, and that this entire thing is 546 meters squared, because that's the area that it gives you. What you do in this case is you combine geometry with algebra to solve this problem. We know the area of this entire thing. We don't know the area of this. So how would you find it? Well, let's think about this logically. The formula for an area for a rectangle or a square is always length times width. We have length here and we have width here, but that's for this small space. How would you find the length and width here? Well, we know that this is X and this is X, but also this is X. So if you think about it, 25 plus 2X would be this entire side, and 20 plus 2X would be this entire side. So that means that 25 times 2x and 20 plus 2x is equal to 546. All I did here was I just used the information that I knew to get what I needed to get to solve this problem. And now all you need to do is to solve this equation. So let's solve this equation together. First thing you need to do is to FOIL. You do this first, and then you do this. So you can do 25 times 20, which is 500, plus 50x, plus 40x, plus 4x, plus 4x squared. And then don't forget about the 546 on the other side. Sorry, my cursor's not cooperating. Don't forget about the 546. If you bring this over, you should get 4x squared plus 90x minus 46. So what can you do here? What I would do is first factor. Then use the grouping that we know to actually solve the problem. So what are two numbers that will multiply to negative 46 but add up to 45? Well, that's just going to be, don't forget the 2 minus x minus 23. If you watched our factoring video, you should obviously know what I'm doing right now. And then after, you just split it up. Here, what I'm going to do is I'm going to clear some room here so I can finish solving this problem. Oh, did not mean to do that. Let me go back to the regular and to get rid of this again. Okay. Alright, so let's finish simplifying this on this side. That would be 2x, x plus, let's see, 23. And then on this side, that's just minus 1, x plus 23. So that means this would equal 2, and then 2x minus 1, x plus 23. So that means your x values would be 1/2 and negative 23. And obviously, you can't use a negative length value, so your answer here should be 1/2. And 0.5 is the same as 1/2, so that's your answer. Alright, 29. In the figure shown, A and BD intersected at point C. Which of the following additional piece of information is not sufficient to prove that A, B, and C is similar to EDC? Okay, great. So glad that this question came up. This is talking about the idea of similar triangles. Similar triangles are triangles that have the same proportions but are not the same size. So what I mean by that, so let's say this is 2, 3, and 4. A similar triangle would be 4, 6, and 8. Because it's the exact same proportion, just that everything else was multiplied by 2. So how do you know when you have a similar triangle? Well, there's a couple rules that you can use to actually know. So let's see if any of these fill those. The first, AB is parallel to ED. Well, let's see. If we know that AB is parallel to BD, let's first draw this diagram. This is not an exact diagram, but A, B, and C. Okay, first thing, we know that these angles are equal. Also, if we assume that AB is parallel to ED, then it also means that these two angles would be equal, and these two angles would be equal because they're alternate angles. Why is that important? This gives us one of the ways we know that two triangles are similar, and that's angle, angle, angle. When you have an angle, 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 and all three angles are the same, then the triangle has to be similar. In fact, you only need to know that two of the angles are the same to prove similarity, because if you think about it, if there's 180 degrees in a triangle, and two of the angles are the same in each triangle, the last one just has to be the same angle for both of them. So since this triangle has three of the same angles, it does prove that it's similar, so A cannot be the answer. So let's look at the next choice. The measure of angle D is equal to the measure of angle B. Once again, that doesn't work because if you have two angles that are the same in similar triangles, you know that they're similar. Okay, C. The length of AB is equal to the length of DE. Okay, so this provides us with, C, one of the other cases. And then let's look at D real quick, because I believe C is the wrong answer, but we need to read D to kind of like get a sense of it. D, the measure of angle A is equal to the measure of angle B. Measure of angle D is equal to the measure of angle E. All right, so in this case, the answer has to be D, and I will explain to you why. So the reason I was thinking about C a little bit is because there's a couple of other ways that we can prove that triangles are similar. And these are, I kind of remember them by calling them the angles and sides properties. Basically in geometry, you'll have these, I guess, patterns that you'll see in triangles. And if you see these patterns, then you know that the triangles have to be similar. Okay, the first one is side, side, side. These examples don't come up in this question, but I just want to show you guys all the options. If each triangle has everything that's the same, then obviously it's going to be similar. The next one is angle, side, angle. So if a triangle has two same angles and one same side, then it has to be similar. Another one is side, angle, side. So if you have a triangle that has two sides that are the same, and one angle that's different, then it has to be similar. And then the next one is angle, angle, side. So if you have two angles that are the same, and one side that's different, then you know that it has to be the same. So if we know that the length of AB is equal to the length of DE, we know that BA and ED are the same length. And we also know that angle C is the same. However, that doesn't really prove anything, because you don't have another side or another angle to make the congruency or similarity statement come true. On the other hand, D does make sure or show that you have a similar triangle, because like I said before, similar triangles are all about proportionality. Because these two triangles have the measure of angle A equaling the measure of angle B, and the measure of angle E equaling the measure of angle D, and because they share an angle in the middle, you can just logically tell that they're proportional. So D just cannot be the correct answer. Alright, so final page, we're going to go through some of these questions. These are the last two ones we have, and they are about circles. First one, point P is the center of a circle in the figure above. What is the value of X? We literally just went over this problem not very long ago. Remember, inscribed circles, and the angle of the center is twice that of the inscribed circle. And this also, solving this problem, like a lot of other SAT problems, you kind of have to get a little bit creative. So as always, let's start by drawing the shape. We have the circle. This is not a great circle, but we have, that's definitely not going to cut it. We have this thing that's like this. Okay, so we have this circle, and then we have this weird thing that goes through the center, and we're trying to find the angle of this. And we have a triangle like this. We know that this is 20, and we know that this is 20. What I would recommend is splitting these into two triangles. Because if you do that, then this basically becomes an isosceles triangle. Like, look back at this example. If you draw a line between A and P, then these two sides are just equal. And one property about isosceles triangles is that the angles on the two sides where they're equal, so in between this area and in between this area, will be the same. And if you split this in half, you have a 20 here and a 20 here, and that means it's 40. And since you know that, I guess, P has, and the angle here has to be twice that of here, you just do 40 times 2, and your answer is 80. All right, the final problem. A circle above with center O is a circumference of 36. What is the length of minor arc AC? Okay, The most important thing here is the fact that there is a right angle here. That means this represents 90 degrees in the circle. And as we saw when we were practicing and learning, the center angle of a circle is directly proportional to the arc length, so AC in this case. So 90 degrees is 1/4 of the circle's total angle. So that means that this thing has to be 1/4 of the circle's entire circumference. So very simple. The only thing you do in this problem is divide 36 by 4, and the answer that you get is 9. So your answer here is A. Alright, hopefully you guys learned a couple things from this geometry video. As always, if you have any questions, feel free to contact me, and thank you so much for tuning into this video.